connecting the voltmeter across this point, it will complete the circuit, which will allow a small current to flow. The resistance of the voltmeter is much greater than that of any other component in the circuit. So, in effect, it will read all of the applied voltage. If you were to connect the voltmeter across the lamp, you would get the same indication as you would across the resistor. Again, the reason for this is the open does not allow current to flow. Keep in mind that you'll only connect a voltmeter across one component at a time. So the rule still applies. When you have an open in the circuit, regardless of whether it's a component or an open wire, by connecting a voltmeter across that open, you'll read the applied voltage. You might say that when you find your applied voltage within the circuit, you have found your open. Voltage across good components in series with the open will be 0. You have a circuit like this one under number 4 on your response sheet. Complete all of item 4 on your sheet. You should have answered that the light would not be lit and that meter 1 would read 0 volts, while meter number 2 would read the battery voltage. Electrically, this circuit is identical to and the resistor. Now I'll break the circuit and see what happens. By opening the lead between the resistor and the lamp went out. So your response should have been something to the effect that the lamp will not light. I've given you quite a bit on open circuits. Their symptoms should be pretty clear in your mind. I'll talk about opens a little more in the latter part of this lesson. But now let's go to another trouble that is common in electrical circuits, the subject of shorts. You have seen how an open stops current flow. Shorts, on the other hand, produce just the opposite effect. A short across a series component produces a larger than normal current flow. Let me show you some examples of shorts. We'll use this component as our first example of a short. Connecting the two terminals of a resistor together by a piece of wire, we'll short out the resistor, and the value of the resistor will not be felt in the circuit. Connecting the two leads of a battery together will cause a short and produce a high current. If this current is allowed to flow for too long a time, it will completely discharge the battery. Another example of a short is two bare wires in a circuit touching each other. Also, improper wiring could cause a short. Here, both leads of the battery are connected to the same terminal of a resistor. This amounts to connecting the leads together and again could damage the battery. So, a power source needs some resistance in the circuit. This resistance will regulate the current and keep it down to a normal value. Shorting across the resistor will eliminate its effect, and there will be no regulation. This will allow a very large current to flow in the circuit. A short amounts to connecting two conductors of a circuit through a very low resistance. In this case, the two conductors are the wires connected from the battery terminals to the terminals of the resistor. The low resistance is the wire that connects the terminals of the resistors together. And now you do this one. It's listed as number 5 on your response sheet. You should have completed this statement, so it would read, a short is a connection of two conductors of a circuit through a very low resistance. Let me review the main points you've learned about shorts so far. First, you learned that a short is a low resistance path connecting two conductors of a circuit. Then you learned that if a resistor connected across the voltage source was shorted, the circuit current would become much greater than normal. Now let's take this idea a step further by analyzing what would happen when another circuit component is connected in series with a shorted one. This circuit is designed to light a lamp. Since the resistance of the lamp is normally low, a resistor is connected in series with it to control or limit the amount of current flowing through the lamp. Now, if the resistor you see was shorted out, the total circuit resistance would decrease and the current would increase. This increase in current would cause the lamp to become much brighter. If the battery voltage was high enough, the current could increase to a point where it could destroy the lamp unless the circuit is properly fused. You learned in an earlier lesson that most circuits are protected against excessive current by the use of a fuse. Remember, the fuse is designed to open the circuit when the current exceeds the rated values for the components in the circuit. This circuit is the same as the one I explained before. It has a 5-ohm resistor connected in series with a small lamp. Since the resistor is limiting the current, the brightness of the lamp is less than what it could be. But we'll call this brightness normal for the lamp. Now I'll short out this resistor. Note the effect on the lamp. Notice that the brightness of the lamp is much greater now than it was before I shorted the resistor. Now we can make this statement. When a good component in series with another good component becomes shorted, the circuit current will increase. This increase in current will not flow through the shorted circuit component, but it will flow through the good component. And now do number 6 on your response sheet. In the first blank, you should have recorded brighter. To explain your answer, you should have something to the effect that the increase in current caused the lamp to burn brighter. In this circuit, I have 3 resistors connected in series. If I short out one of them, the current will increase. With this short across R3, it's no longer in the circuit, and the total resistance is made up of R1 and R2, which is less than all 3 resistors combined. This accounts for the increase in total current. Now, if I short out R2, the current would increase even more. With R2 and R3 shorted, the total resistance in this circuit is made up of R1 only. So regardless of the number of components you have in a series circuit, shorting out one of them will cause the current in the circuit to increase. Shorting out another component will cause the current to increase even more. In other words, as you short out components, you decrease the total resistance in the circuit and increase the current. Now, do number 7 on your response sheet. Your response should be, current will increase. By now you should be well grounded on what readings you'll get by connecting a voltmeter across an open or a shorted component. You'll have to use these indications to tell whether the component has an open or is shorted. And now let's analyze this circuit. When the voltmeter is connected across R1, it indicates 55 volts. When the meter is connected across L1, it indicates 35 volts. When the voltmeter is connected across R2, it indicates 0 volts. Now, what trouble or troubles would there have to be in this circuit to give these indications? Think about it for a moment. Since we have a voltage across R1 and L1, we know they are neither open nor shorted. But how about R2? If it was open, we'd read the applied voltage and would not have any voltage indicated across R1 or L1. There cannot be any voltage across a short, since a short is a very low resistance. Therefore, R2 is shorted. Then in this circuit, we have one short and no open components. Do this one. It's listed as number 8 on your response sheet. In the first blank, you should have none or something to the effect that there are no opens in the circuit. In the second blank, you should have R1.